Next talk, Stefan Gerth. Where are you, Stefan? And we'll talk about automated segmentation, there you go, of potato tuber computed tomography measurements for non-destructive biomass determination. Now you don't have to say it.
Thank you. Okay, so thank you very much for the opportunity to talk here. In the last talk there was also a bit about X-ray computed tomography, and I would like to show how this can also be completely automated, applied for biomass determination of potato tubers in soil. So first, why computed tomography? It was already introduced very well. What is the benefit of computed tomography? Then I would shortly show how the setups look like in our system, how measurement is typically conducted, and what this 3D reconstruction tells you physically about your data set. And afterwards I will show the drought experiments we did and a short conclusion. So first, why computed tomography? If you normally go for below ground organs, what you have to do for each time point, you have to dig out your plant, and then, for example, count or measure the volume of individual tubers, and as a function of time. But of course, you will never measure ever the same plant, and so you can only get a very diverse statistics how different plants behave over time. So the benefit of computed tomography, as already mentioned, is that X-ray light is able to penetrate like matter. So it's not blocked by the surface as the visible light, because we go to much higher energy or shorter wavelengths. If you here look, that's the visible light, which is typically used for optical imaging, and then the UV and the infrared rays and the X-rays, it's even more energy and capable of penetrating the material. So what you can do is actually, you can put in a pot with some tubers in there, penetrate the complete pot, do the 3D reconstruction, and get information about the inner structure of your pot. And now the task is, of course, find a good way to completely automatically separate each individual tuber and measure this tuber. And then what you can do is you can track them over time to see how each individual tuber, like this one, is evolving as a function of time in the pot. So how such a system looks like in our case, we have here, it's the other way around, so in the last talk the X-ray source was on the right hand side, we have it on the left hand side, so I should have taken the picture in the other way around. So. But our X-ray source is located here. We have a pot directly located in front of the detector, because there are different approaches how you can do the measurements, and we were choosing like a detector limited resolution approach, which allows us for fast measurement time. So each measurement time here in there is about a maximum of 5 minutes. So in 5 minutes we can get like the complete 3D reconstruction of the pot and the attenuation of the X-ray. So if the X-ray is penetrating your pot, it's attenuated, and the amount of the attenuation is dependent, of course, of the X-ray spectrum, like the diversity of the range of wavelengths, X-ray wavelengths you apply to the pot. The material in the pot, like the soil, the stones, the organic matter, and the density. So what you can do is now you can reconstruct this whole thing, and then make just a virtual cross section in there to visualize the distribution of gray values within your pot. And what you can see here now, it's just a horizontal slice within your pot, and clearly you are able to identify a tuber, the potato tuber in there. And the gray values you will see here, they are a combination of like the material, the atomic composition of the material, and the density. And the good thing actually about this is because plants has a very homogeneous atomic composition, so they are more or less always hydrocarbons. What we measure here for plant parts is only more or less the density. So it's a physical measure in the reconstruction of the density of your material, and at the same time you can measure the volume. So what you have is a tool measuring mass, the mass of an object within your pot. Of course, a stone has a complete different atomical composition, so this you cannot compare because therefore you need to correct for the atomic elements in there. So how was our stress experiment designed? So we have two growth chambers in our facility. So in the control batch we had 16 hours light and 8 hours dark, and 21 degree during the day and 19 degree during night, with about 100% watering, so regularly watering. And within the stress period we increased the temperature to 29 degree during the day and 21 degree in night, and reduced the watering to 50% of the typical water uptake we applied. And so we did a control measurement and a combined heat drought study where we applied the starting of the stress as soon as we were sure that in each pot there is a tuber already. So it's not just a time point which is chosen by chance. So we were waiting that in each pot we have at least one tuber already induced, and that was the start of our stress experiment. And then we were waiting for 2 weeks doing the stress experiment, and within the stress we had some more pots which we did some destructive harvesting for metabolomic studies and doing like cross-referencing like destructive analysis to see how good our prediction of biomass in the end will be. So we started with a variety diamond, 8 pots under stress condition and 8 pots under control condition, which were measured regularly, and 4 additional pots for the destructive harvesting. So, and now thinking, okay, the first what you can do is integrate the biomass of each pot and look how it will evolve over time. So what you can see is, like for the control measurement, the evolve over time of biomass, so that's the mean biomass per pot. And for the stress, heat and drought stress experiment, you see there was a stagnation in the biomass increase, and after releasing the stress there was an increase again. So what you of course can do as well is, like, you can directly calculate the growth rate, because it's a non-destructive method and we know what is the stage at our first measurement time point, and the next we can calculate just the rate of growth. And you can see directly, starting at day 20 here, our stress, the growth rate were stagnating and decreasing up down to 0 within the 2 weeks. So the growth rate stagnated until 0 growth within 2 weeks, and directly after releasing the stress, there was a big jump in the growth rate again, which was even more than in our control measurement, which was also like a constant growth at this time. And in the end of the measurement, the level of the growth rates were again the same. So now looking what the density, as I told you, we can now check for the density or the attenuation within each object, how this behaves. And what we can see now in the drought experiment, we got earlier already tubers in there. So that's a chamber effect, which was, of course, we could know that there will be some chamber effects, but here we have about 2 days or 2 measurement points, which are at least a week difference in the tuber initiation for the chamber, which were later on stressed, and the chamber which was in our controlled condition. Of course, if we now compare afterwards with destructive measurements, you will never see this failure, because you couldn't know that in the chamber, in the growth chamber, which were later on stressed, the initiation of the tubers was earlier on, and therefore there was like a growth advantage for all tubers within the heat and drought stress environment. But what's also visible, directly stressing the plants, there's an increase in density, and this was a little bit counterintuitive for ourselves, because what we measure there is the density, is like also as the attenuation is the water and the hydrocarbons and anything else, and expecting like in a heat and drought stress environment that there is a water loss in the tuber, which will reduce normally, or in my opinion the first thing, it will go to a decrease in the attenuation, meaning you lose water, but there was still an increase. And our colleagues from the university in Erlangen were doing some SUSI studies to see how active actually the starch transportation still is. And there was an indication, actually, or is an indication, that the starch transport is still active in a heat drought environment, so that starch is still really in a high amount put into the tubers. Might be like an effect to save the starch for the next generation in the tubers. And you can see this in an increase in the attenuation. But having all this data together, what we can now do is afterwards, with the destructive sampling, we can look for how this attenuation times the volume we've measured is correlating with the fresh weight or the dry weight. And doing this for the fresh weight, we got a correlation of R square 0.94 and 0.99 for the fresh weight. For the fresh weight with 0.99 and 0.94 with the dry weight. So that's like now our possibility to transfer our volume and the measured attenuation to a virtual measured biomass. And this you can now do for each measurement we've done. And here it's just an example of the growth and transfer to gram in fresh weight for each individual tuber within a pot as a function of the days after the tuber induction of the first pot. So, okay. So, as mentioned, what we did afterwards was also destructive harvesting. And looking for destructive harvesting just by numbers, we could see no differences in growth for the tubers harvested manually for the pots, but knowing afterwards there's a really big effect of our chambers that we have about 1 week's growth advances for the tubers, which were later on stressed. We could say, okay, this might explain this, that within the stress period there's not a big difference between the control measurement and between the stressed measurement. But now we can do the same thing, calculating for every tuber in every pot we've measured with our virtual biomass, and you can see, okay, going for all of the tubers we have in our batch in all of the 8 pots, the difference is not that big of the mean difference of the effect of our growth chamber, and you clearly can see the loss of the virtual biomass over during the stress period and at the end of the experiment as well. So our second experiment was now to do the same thing for different varieties. And because we know that in the starting phase we don't need to make a high sampling frequency, we just waited until in each pot were a tuber available and then started with a high frequency desampling. So you will not see the induction phase in the beginning now. It starts directly with the heat and drought phase, and we didn't do any control measurements afterwards because all of our chambers were filled with the different varieties and we don't only have 2 of them. So in the beginning they were looking like this. In the middle of the drought stress experiment they were growing but looking not that good actually, and in the end they were looking really, really bad actually. And but they were surviving. And so in this experiment we scanned 4 pots each for the different varieties: Agria, Ramses, Tomensa, Saturna and Diamond again. And for each of them what we see was this biphasic growth. It means during the stress phase there was a stagnation in growth, as also already seen for the variety Diamond, and afterward there was a release. And here you can also see the different yield of each tube or the different yield of the mean tuber weight in each pot. And of course also here you can go directly for the growth rates, seeing each genotype directly changes the growth rate, and some of them even shrink. So there was, in some of the varieties you see a shrinkage effect, that the tuber was shrinking. And they respond after releasing the stress completely different. So you see one variety is really overshooting the growth rate and another variety is very slowly going back to the mean value afterwards. Also the attenuation coefficients, what we've seen in the variety Diamond in the beginning, that the attenuation coefficient increases during the heat and drought stress phase. I need to hurry up, sorry. was visible for all the varieties, and I jumped to the results and say, okay, what we've done, we found a completely automated imaging pipeline for potato tubers. We can scan 5 minutes for a pod, and afterwards in the background you can run parallel the segmentation and data evaluation algorithm also automatically, which needs about 20 minutes. We couldn't find phenotypic variances in the existence of the biphasic growth, so each of the varieties we scanned showed a biphasic growth behavior, but there was a genotypic difference in the increase of the growth speed after releasing of the stress. And using the CT attenuation parameter, the physical measurement of the CT allows us really to transfer the volume into a virtual biomass, which catches up pretty nicely with destructive measurements. So thank you very much.
I'm going to suggest that if you have a question for Stefan, you catch him in the coffee break. You went a little bit too over time. Thank you very much. I'm sure you'll catch him.